forgot to push record. So tap water. What's tap water a mixture of? Does anybody know? Chlorine, chloride, fluoride, and whatever else is in there, right? Who knows? And depending on where you drink your tap water, it tastes different, right? And sometimes you get used to the tap water at your house and you go to someone else's house and think, oh, this water's nasty or whatever. But generally, tap water's nasty, right? All right, any questions on how to tell if a substance is pure versus a mixture? Good? All right. Now there's two types of mixtures. We have homogeneous or homogeneous, depends on who says it. I don't know the proper way, but okay. And we have heterogeneous. They're both genius, right? Not that kind, but okay. Different prefixes. So what does the prefix homo mean? Same, right? Homosexual, same sex, right? Homogeneous, same what? Same genes, right? Not quite. Sounds like it. But homogeneous, and these are both mixtures, right? These are both mixtures. So a homogeneous mixture is a mixture and do we know what a mixture is? I didn't give you that definition.
Two different things.
Two or more substances, or two or more what? Because a homogeneous mixture is a substance, right? So we got a pure substance versus a mixture. We'll just call it a substance. So two or more substances make up a mixture, right? So a mixture that is uniform throughout. And we will go over some examples in just a minute. I'll just give you straight definitions real quick. So what's hetero mean? Different, right? So this is a mixture. Heterogeneous is a mixture that is not uniform throughout. Has anybody ever heard homogeneous being used out in life? Where have you seen it?
Yes, I heard it in other classes.
Okay. Yeah.
Pronounced differently, but like homogeneous,
Yep,
meaning,
same.
mixed fully.
Okay. What? Okay. Good. In other classes, I'm sure you've heard it, but what about in life in general? Has anybody ever come across it? All right, that's no big deal. When I was growing up, we drank milk. I don't know if you guys drink milk, but if you look on the jug, there's a sticker that says homogenized. Has anybody ever had raw milk? Milk straight from the cow? I mean, not straight, but okay. You have to milk it and then without it being processed or anything. Has anybody ever had that? And you set it on the counter, what happens? The cream rises to the top, right? It's not homogeneous or homogenized. So what they do is they boil it. What was it called? Pasteurize. Yep, they pasteurize it, and then it homogenizes the milk, makes it all one. So you set it down in a jug on the counter or in the fridge, and it doesn't separate. Good. All right, so let's go through some examples here. So let's deal with substances here. All right, salt water. Homogeneous or heterogeneous? Yeah, why? That's right, why?
They're two different substances that have been mixed together fully.
Okay. When you say fully, you mean?
The salt dissolved and combined with the water.
It's
Okay, good.
dissolved completely.
It's dissolved and it's the same throughout. How do we know it's the same throughout? Do we just get our little meter in there and tells us, okay, this is homogeneous, this is homogeneous? Well, what? You can separate it. In fact, we better give you a better definition of a mixture. Okay? Right here. I'll just put it right here. Let's do a different color. So a mixture is when you have two or more substances that can be separated physically. What does that mean? You can grab it and take it out. Well, you can't do that with water, can you?
Well, I know that in survival shows, sometimes what they do is they take like ocean water and then they make a sort of contraption where they boil the water.
That's
and then
right.
it collects, leaving the salt behind.
Is boiling water a physical process or a chemical process?
Physical?
It is physical. We have two different boiling points for water and salt. You boil it, water's going to come off and leave the salt behind, right? So that is a physical process. That's what I mean when we say we can separate it physically. What about water? Can we separate water into H and O? We can. Can we do it physically?
Yes.
How do we do that?
Electrolysis?
Yes, and that's not physically. That's chemically. During a chemical reaction, we can separate those. Does that make sense? The difference between those? Okay. So if you can separate them using physical properties, then it's a mixture. If you cannot, and compounds, you cannot. You can't separate the atoms physically. You'd have to do it chemically. Does that make sense? So good. So salt water is homogeneous. Why? Because you can separate them. That tells us it's a mixture, right? But how do we know it's homogeneous versus heterogeneous? Because you can also separate heterogeneous mixtures. Well, get a cup of salt water from the ocean, right? You guys ever go to the ocean? Well, you don't have to get a cup. You just go there and you get a little bit in your mouth, right?
Mm-hmm.
And then a little bit down the little bit of ways, you get a little bit more in your mouth. Does it taste the same salty? Yeah, it's pretty much the same throughout, right? You're not gonna come over here and, whoa, that's way saltier. Oh, that's not very salty at all. It's all the same salty. Does that make sense? And you're not always going to be able to taste the stuff to see, but it's all mixed throughout the same. Does that make sense? Okay, what about sodium carbonate? Homogeneous, heterogeneous, or pure substance?
Pure substance?
Pure substance. This is just a compound, right? Na2CO3. Right? Do you remember how to write those? You're going to need to remember how to write those for the rest of the semester. Took a midterm, but we still need to know that stuff. Okay, so don't forget it. Yeah, this is a pure substance, not a mixture. Good? What about dirt?
Heterogeneous.
Why?
Because there's different, like metals and different types of,
Rocks or,
yeah.
yeah.
It's not uniform.
It's not uniform. You take one handful and another handful, and this might have a big clump of whatever in it, and this might not, right? They're not uniform, so that's heterogeneous. Good. What about soda? Like soft drink? Homogeneous. Every taste tastes the same, right? Until you let it sit out for long enough, and then the carbonation goes away, right? But if you drink it at the same time, homogeneous. Good? What about salad?
Heterogeneous.
Heterogeneous. Every bite's not going to have the same amount of tomatoes in it, right?
Does anybody actually like tomatoes in their salad?
I do.
Oh.
Cherry tomatoes.
If it doesn't have tomatoes, I don't want to eat it. It's a good thing we're all different, huh? Okay. What about granite? You guys don't, have you ever had a granite countertop? Hetero, why? Why do you say that? Because what?
Is it a conglomerate or is it like a mixture of different, like?
A mixture of different rocks, right? Yeah. So granite is heterogeneous. What about steel? Is steel a mixture or a pure substance? What? Mixture? Do we see steel on the periodic table? No, this is a mixture of different metals melted together. Can we separate them?
Isn't it tin and something?
It's iron, carbon, chromium. Well, it's only chromium if it's stainless steel. So it might be nickel, I can't remember. But it's different elements.
Tin is copper and bronze. That's where I was confused.
You can separate them because they should have different melting points.
Because they have different melting points, that's right. If they have different physical properties and you can melt them at different temperatures, pull them off. And I'm not saying it's easy to separate them, but you can, right? And what about helium? Real loud? Pure substance. This is number 2 on the periodic table. It's an element. Remember, if it's an element or a compound, it's a pure substance. Good? Any questions on homogeneous, heterogeneous versus pure substance? Good? All right. So that was kind of a little bit of information before we get into today's topic, which is solutions, aqueous solutions. So when I say solution, I'm not talking about the answer to a math problem, right? So, you guys ever heard of solutions before? Like a salt solution. What am I talking about?
A mixture of salt and something else?
A mixture of salt and something else, yeah. So, a solution is a mixture. What type of mixture would you guess it to be? Homogeneous or heterogeneous? Homogeneous, right? Homogeneous. So it is a homogeneous mixture. It's probably homogeneous, but I'm so used to just saying homogeneous. Is that okay? A homogeneous mixture containing at least two substances. Whoa. Obviously, because it's a mixture, right? And these two substances, one of them is a solute. Solute is the stuff dissolved in the solution. The substance dissolved, and the solvent is the stuff that dissolves, right? The dissolver. Good? Does that make sense? You guys ever heard of a solvent before today?
Yes.
Where have you heard it?
Water.
Water is a solvent. It is a universal solvent because you did your reading. Did you? Awesome. Has anybody ever heard of a solvent before coming to chemistry? What do you think of when you hear the word solvent? I'll tell you if you tell me.
Something that dilutes, basically.
Okay.
Chocolate milk. I think of chocolate milk. I think of the milk as the solvent.
Okay.
That I usually get from the
Huh. A lot different than my experiences, but that's okay. Go ahead. Is soap a solvent? Yeah. Soap could be a solvent. Now, when I was 15 years, you guys want to hear a story? When I was 15 years old, I worked at a print shop where they print on paper, right? Put ink on paper and usually letterhead or business card or whatever, right? Flyers. And when I was 15, I was just a young kid working there, taking the garbages out. And the guy working on the press, he says, "Hey, do you want to learn how to do this?" And I said, "Yeah, it's way better than throwing the garbages out, right?" So he says, "Okay, I'm going to show you how to clean this out. Because if you don't clean the press out, you're going to ruin the rollers and you can't print anything, right?" So this is a little bit different than the printers you guys have at home, right? Where you buy the print cartridges and you stick them in and they spray ink down, right? So anyway, he says, "Okay, what you got to do, you got to put this little thing in to scrape all the ink out. And you put this," he called it solvent. This is my first experience with the word solvent. And he says, "Okay, you got to spray this in here. And it dissolves the ink out. You guys ever get ink on your hand from a broken pen or something? You just go wash it under the sink, right? And it just comes right off? No way. It does not come off. It's like oil, right? It has oil in it, and oil doesn't mix with water, and so it just doesn't come off. So we put the solvent in it, and the solvent dissolves the oil, or the oil-based ink, right? And I don't even know what the chemical formula of this solvent is. We just called it solvent, right? And anyway, so here's another part of that story that's kind of comical. He says, okay, hey, we need some more of the solvent. He had a 5-gallon bucket here with solvent in it, and then we put it in a little squirt bottle to squirt it in the press, you know. And he says, hey, we're out of this solvent. Out and back, there's a 55-gallon drum, and I need you to just go fill it in. You know how to siphon, right? I said, yeah, I know how to siphon. Everybody knows how to siphon. Watch it on TV, they go, right? That's siphoning. And so I just says, yeah, I know how to siphon. It's okay, there's a hose out back there. No, he says, here's the hose. Go back there and fill this 5-gallon bucket up. I said, okay. So I go out there and grab it, put it in there, and this stuff has fumes that are just killing me, right? And it didn't work the first time. Or the second or third or fourth time. And I'm over here dying. And he comes out there, what's taking some money? He saw me what I was doing. He said, stop. Now, I'm a physics teacher, but I didn't know physics back then, right? So all you have to do is put the whole hose down in. We all know how to do this. We've done it with straws, right? You go like this and whoop, right? But oh man. So I wasn't using my finger. Anyway, so you just grab it and it comes right out and nice and easy. Don't do that on somebody's car though, okay? All right. Actually, they usually have a lock on cars nowadays, but anyway, that's my experience with solvents. So what do solvents do? They dissolve, right? So can soap be a solvent? Does soap dissolve stuff? What do you use soap for? To get
Crud off your hands.
oil or ink, right? Mm-hmm. Right? Yeah, it's a solvent. Are we good? All right, so there's a few. In fact, let me just give you a few more points here. So a solvent is the majority of the solution. And solute is the lesser portion of it. Okay. Let me give you 3 points about a solution that you need to know. First one, so a solution can be liquid, gas, or a solid. You think of a solution being a solid ever?
Solid.
What is it?
Solid.
Real loud.
Solid. Saying salt.
Salt? What about steel? What is steel? What kind of mixture is steel?
It's
Homogeneous or heterogeneous?
heterogeneous.
Look at this. The steel, are they the same?
Yes.
All the way through?
Yes.
Yeah, they're the same. It's a homogeneous mixture. This is a solution, okay? So it could be liquid, gas, or solid. So an example of solid is steel or brass, okay? And gas, what's an example of a solution made of gas? We deal with it every day, all day long.
Air.
Not oxygen is a what? Pure substance, because it's on the periodic table. But air, Air is a mixture of what? Mostly what? Nitrogen. Like 78% nitrogen, 21% oxygen, and then a little bit of argon and carbon dioxide and water, right? Whatever else. And liquid, most of them are going to be liquid. When we talk about in this class, most of them are going to be liquid. Because like Vid mentioned, that water, let me use a different color here. Water is a universal solvent. Most of the time when we have solutions, it's a solution of water, or water is the solvent. Like when you make Kool-Aid. I don't know if you guys have made Kool-Aid. I haven't made it since I was little, but okay. You make Kool-Aid, and, well, most of it's water, right? Put a little pouch in there and some sugar and water, right? Most of it's water. Okay, the next point that you need to know. The dissolved solute will never settle out or separate. Kind of like when you put a gallon of raw milk on the countertop, the cream rises, it separates, right? So that is not a solution. It's not a homogeneous mixture.
Why do they call it heavy cream if it's what floats to the top of the milk?
Because it's heavier than normal, is my guess. So dissolved solute does not separate out. Separate. Okay. And the last one, the solute particles are solvated by solvent. Okay, now that's a word that we probably don't know what it means, right? Solvated means it's completely surrounded. I'm spelling that wrong. Completely surrounded.
So just to be clear, solute particles are solvated by
Solvent. So
Okay.
completely surrounded by solvent. So you throw salt in water, what happens? What actually happens, we'll talk about this a little later, but what actually happens is the sodium and the chloride, so sodium chloride is salt, sodium and the chloride break apart. Now, if they break apart, they got positive and negative, and they want to attract, right? So they're not just going to break apart if they're going to be alone. What happens, remember, water is polar or nonpolar? It's polar. That means it has a partial positive end and partial negative end, right? The partial positive end of the water is attracted to the chloride, the negatively charged chloride. And the positively charged part of water, hydrogen, the negatively charged part of water, oxygen, is attracted to the positive sodium. And it completely surrounds it. When it completely surrounds each particle, that's what solvation is. Okay, and we'll bring that up a little bit later, a little bit more detail.
One time I made Kool-Aid and I decided to add more sugar into it, and I ended up adding so much sugar that it wouldn't dissolve, and it just sort of pooled at the bottom. So
We'll talk
that's
about that too.
wonderful,
Yeah. Yep.
because there wasn't enough solvent.
That's right. You can only fit so much in there. All right, let's do some practice. So we got a solution, and we want to know which part of the solution is the solute and which part is the solvent. So we talked about this just a minute ago, but let's do it again. Air. Because this might be on the test, guys. Okay. Which part is the majority, the solute or the solvent?
The solvent.
The solvent is the majority. So what part of air is the solvent? Nitrogen. Nitrogen gas, right? And what is the solute? Oxygen, argon, carbon dioxide, whatever's in there, right? Okay. Okay, what about soda? Water is what? The solvent. Yeah, most of it's water, right? So we could just drink a bunch of soda and we won't ever get dehydrated, right? Unfortunately, it doesn't work that way. My son-in-law just pounds sodas all the time, and he doesn't ever drink water. Went into the emergency room because he was dehydrated. All right. So what's the solute? What's dissolved in water? What is it?
Salt, sugar.
Carbon dioxide. Good. Sugar and flavor. Yeah, whatever.
There's a surprising amount of salt in soda.
Is there?
Yeah. Like one soda is, dang it, I had it on my head, but now I can't remember.
Yeah, there might be salt in there too, right? And there's probably all kinds of crap they put in there nowadays, right? Back in the good old days, they just had 3 substances. No. All right, what about rubbing alcohol? Water's the solvent? Not quite. C3H8O, isopropyl alcohol, which is the name of rubbing alcohol, is the solvent. That's the majority of it. If you look on the bottle, what does the bottle say? It says don't drink. 70% alcohol or 90% alcohol, whatever it is, right? You can get a different concentrations. What's the rest of it? What's dissolved in the alcohol? Water. In this case, water is the solute because it's the minority of it. Make sense? All right. What about brass? Anybody know the majority of brass? What's copper? Yep. And what's it a mixture of? Copper and what? What?
Tin? Or no?
Not quite. Zinc. Want to go over more examples? How are we feeling? More? Yeah. More or we're good? One more? Okay, so we got tea, vinegar, gasoline. Which one?
Wait, tea, vinegar, or gasoline?
Or gasoline, yep.
Tea, I know are pretty good.
Oh, you know it?
Yeah, it's water and tea leaves.
Okay, good. What about gasoline? It's not methane. Methane is a different gas. So the majority of gasoline is octane.
That was like
The additive.
stability level. Like you could choose like 93 octane.
If it's 93, does that mean it's 93% octane?
I thought it was like its susceptibility to like pre-combustion in like the engine or something like that. Like it's the higher the number, the less it is.
The less octane it has?
No, the higher the octane number, the less it'll combust before it should. So it's like jet fuel is like 100 octane, so it shouldn't combust like before. Or like diesel is like 100 octane, so it shouldn't combust before. And the other ones are like methane and ethanol and stuff.
I'll have to look that up. I'm not sure.
What if it's that the octane's not what's combusting, but the, what was the other part of gasoline?
Well, there's a lot of different additives in gasoline. And if I'm wrong, then it's some carbon-hydrogen compound, whatever it is. I thought it was octane, but yeah, I'll have to look that up. Could be wrong. But it's some carbon-hydrogen compound. Just like methane is CH4. And then propane is C3H8. Butane, C4H16H. I don't remember. But it's all carbon-hydrogen compounds are extremely flammable. Okay? No, I shouldn't say all, but and vinegar is what? Mostly what? What?
An acid.
It is an acid. So what's the majority of it? What's the solvent?
Water?
Water. So if you look on a bottle of vinegar you buy from the store, it's 25% acetic acid. That means 75% of it is water. So we got water and acetic acid, which is HC2H3O2.
Doesn't vinegar come from wine?
You can probably get it a few different places, but all right, we good there? I didn't put any worksheets out today. Oops. All right, a few more vocabulary words. Solubility. Heck. Solubility is when the solute's concentration is at its maximum. So the dissolved, when the amount of solute dissolved in the solution is at its maximum. So that means you can't put any more stuff. And like you put more sugar in it, it just doesn't dissolve, right?
Yeah.
You've overreached the solubility. Does that make sense?
I wonder why it still gets wet though. I guess it's because it's in water, that's why it gets wet.
That's right. Okay, saturated solution is a solution that reaches its solubility level. So basically the same as this, right? So it's a solution that contains the maximum amount of solute. And when I say the maximum amount, that also depends on, I should write it right here. at given conditions. Because you can change the conditions like the temperature and the pressure, and you can dissolve more in, right?
So if I boiled the Kool-Aid, then it might be able
That's
to
right.
accept more sugar.
But then you let it cool, what's going to happen?
Sugar's gonna pool at the bottom?
That's right. So saturated solution is when the solute concentration equals the solubility. Come on. Does that make sense, guys? Yeah, question.
Why does it, like, why won't it just, like, if there's more water and there's a bunch of liquid, why won't the sugar just, like, dissolve in there?
Good question. You know, why doesn't it dissolve? And we talked a little bit about this, and we'll talk a little bit more. Remember solvation, where the solvent completely surrounds each particle of solute? Well, if all the water surrounds all the different particles of sugar, and there's no more water to surround any more sugar, then that sugar will not be dissolved. Does that make sense? And it's overreached the solubility level. Okay, when it's unsaturated, what do you think? Not quite the minimum, but it's less than the maximum. Okay? So anything less than the maximum, you can have one little particle in a 10,000 gallons of water and it's unsaturated, right? Or you can have just barely slightly below solubility level and it's unsaturated. So the solutes concentration is less than the solubility. Good? And what about a supersaturated solution? Any ideas?
That'd be like when you boil the water and you get more sugar, or like you do.
That's right. More than the max, right? When the solute's concentration is more than solubility. And how do you do that? Yeah, change the conditions. You increase the temperature, increase the pressure. By what? Stirring it, yeah. That's right. So let's, uh-oh. There it is. Let me see if I can pull up an example of this. This is cooler in real life, but I don't have it here. So we'll just have to watch a video. How's that?
This is a supersaturated solution of sodium. Supersaturated means it's being unsaturated.
Sorry. I accidentally pressed the wrong button.
Sodium has we can make everything fresh out of sodium.
Is it not showing it? Huh, maybe that's not going to let you see it.
This is a supersaturated solution of sodium acetate. Supersaturated means it's beyond saturation.
Let's do the. It stopped recording. Probably when I turned on the. Darn it. Okay. So, when ionic compounds dissolve, just right here, when they dissolve, this is kind of what happens. So if we have sodium chloride gets thrown in the water, then the sodium will split off from the chlorine. But it won't do this unless there's something else that it can attract to. A greater, well, a more, probably more efficient way to attract. Okay? And so what happens, there's plenty of water in here. So let's make that yellow. You have the sodium is attracted to the negative end of the water, and water completely surrounds it. What's this called again? Almost. Solvation. Solvation is when the solvent completely surrounds the solute particles. And then the chlorine will be attracted to what part of water? The positive end, which is the hydrogen. And you'll do stuff like this on critical chemistry as well. Okay? So it completely surrounded, and that's how you know it dissolves. Sugar, on the other hand, so if we throw, so that's for all ionic compounds. So what we say is the ions dissociate. They break apart, and then they're solvated by water, or the solvent. Okay? For covalent compounds, a little bit different, because they're not made of ions, so they're not going to dissociate. Okay? The only way it's dissolved, let's say in water, has to be a polar substance. So sugar looks something like, and I can be probably way off, but where it has oxygens and hydrogens over here, this is the part that makes sugar what? Polar. Not sweet, but polar. Well, I don't know what part makes it sweet. Probably the combination of it and the structure, right? And it matches. In fact, sugar is like heroin. Very addictive, and it matches, the structure matches the same as what is it called? The same thing. What is it that?
Synapses?
Yeah, but it.
Neural pathways? Receptors.
No, I'm thinking of, yeah.
The brain blood barrier?
Well, all these are the right answers, but I'm trying. I'm thinking of something else. But anyway, that's okay. So it's endorphins or something that makes us want to. Yeah, something that makes us want it more, right? But it's because it's the dopamine. Yeah, that's what. That's because that does cross the brain blood barrier, and it helps us to want to just, I want more, I want more, I want more. And that's why sugar, I mean, we all know, we just want more, we want more. Anybody ever try go off sugar?
It's also a leading
It's
cause of
hard.
heart problems.
What?
It's a leading cause of heart problems.
What is? Sugar? So how does this sugar molecule get dissolved? Well, this part of the water has to surround this part, right? Because the oxygen is the negatively charged part, and so on. But what about the rest of it? What about this stuff over here? Then you have this part over here, right? Attracted to the other parts of it. But anyway, water completely surrounds it, and it's dissolved. It's completely solvated. Does that make sense? What's going on the molecular level? Okay.
Kind of the same for like electrolysis of like water to separate it. They say like you should use like a catalyst, sodium, or what is it, baking powder? How does that work like the opposite, where like it makes it more likely to break, or like the bonds to?
So, what's the example again? Because I don't know
It's
if I.
like you add like baking powder to water,
Uh-huh.
and it makes like the reaction, or you add some powder to water. and
To
it makes-
separate the hydrogen and oxygen.
Yeah, how does that like? How does it
Uh,
work out for like when you do the like on a chemical level? This is more of a physics question, so my apologies. I'm just
No, you're good. I'll have to think about that. Can't give you a good answer right now.
Is it possible to make the bonds between different molecules stronger?
To dissolve it?
Not really to kind of do the opposite of dissolve, make something less dissolvable by,
So what's your question?
or not molecules. Is it possible to just make something less likely to dissolve? The bonds between the parts of it stronger?
Well, that's all about the intermolecular forces, right?
Oh.
So, and that's what this is. We got a hydrogen bonding here, and that's why it'll. So that's why in this case, that's why it'll separate, because hydrogen bonding is a pretty strong. It's not a bond, but it's a strong attraction, right? And so if you have all of these attractions right here, then that's better than just one chlorine, for example. You know what I mean?
Yeah.
And so some substances will partially dissolve, and some substances, most of it won't dissolve because it's kind of less efficient, or you know what I mean?
Yeah.
All right, so the last thing with this topic, man, we're going a little slow today, maybe. You guys are probably thinking, no, we're not. All right, so we talked about how do we get oil off of our pans, let's say. We put soap on it, right? So how does that do that? If like dissolves like, how does soap dissolve both in water and in and in oil?
Because it has like both
That's right. So I'm going to just give you a quick drawing here. So this drawing right here represents, every vertex represents a carbon, right? And on those carbons are bonded with hydrogens, right? This is a carbon-hydrogen compound. This is oil. And soap looks like this. Not exactly, but something kind of like that. Has an oxygen on the end, and it's negatively charged. So this is the polar end, and this is nonpolar, right? And this is nonpolar. And then you got water, which is all polar. So if we not drawing this very well. So there's our soap molecules. And those soap molecules are surrounding, oh, that was weird. Surrounding the oil compound. And then you got your water that surrounds everything else. All the way around. And then it just flushes it all out. Okay. Kind of cool, right? But you try putting water on there and it doesn't do anything, right? But if you just put soap, you got to have the water to push everything out, right? Good? Okay, any questions on solutions? I'm going to talk about solutions today. And we don't have class Thursday because of 4th of July. And the 3rd, tomorrow, is the last day to withdraw from this class. I'm not saying, I'm just giving everybody a reminder. I'm wondering if we ought to touch on the next topic today, just because otherwise it'll just put us behind again. How are we feeling? We're feeling overwhelmed?
Maybe touch on it lightly, but only like a small portion of it.
Who's done today? Who wants more? Okay. Let's see. Let me.
What's the next topic?
This is going to be a bad video. It keeps stopping. All right. Let's say we have 2.5 moles of silver. And we want to know how many atoms of silver do we have. Again, usefulness, this is not a useful calculation, but you will be tested on it. Okay? So I'd get your calculator out. Make sure you can do this. So where do we begin? With what we know, right? 2.5 moles of Ag, and write everything. Don't get sloppy and just write moles, right? Right now, this is simple, but later on, we're going to be doing a chemical equation and going from one substance to a different substance, and if we don't keep track of what we're dealing with, it's going to mess us up, okay? So always include your units, and part of that unit is silver. Okay? Now, do we want moles of silver in our answer? No, so where does it go? On the bottom, right? Well, I don't know. Do we go to grams? I don't know. We want to go to atoms, but we know we don't want moles, right? So the moles go down at the bottom, moles of silver. If we have 1 mole of silver, do we know how many atoms of silver we have?
No, but we know how many particles.
We don't? What's an atom called? A particle of an element. Do you get that? So do we know how many atoms we have in 1 mole of silver? 6.022 times 10 to the 23 atoms of silver. And we can see moles of silver go away. It's just a conversion, guys. This is why we learned conversions right at the beginning, because this is the math of chemistry. If you can do dimensional analysis, you can do everything we're going to do this whole semester. Okay? Can you multiply these together on your calculator and get an answer?
It's in scientific notation.
Okay, yeah, what is it?
1.555 E24, which I think is times 1024.
That's right. So if we round that, it's 1.6. How do we know what to round to? Because this has 2 sig figs, right? How many sig figs does this have?
4.
Infinitely many. Why? Because it's an exact value. There's, for every 1 mole, there's exactly that many. Well, I don't know if it's exact, but okay. Any conversion factor, we don't count in to consider how many sig figs are in our answer. Yeah? So really, that's our only measured value. And so that's going to be atoms of silver. Good? Question?
Could you re-explain how you got that answer from 2.5 and 6 mole?
So do 2.5 in your calculator times, do you know how to multiply by scientific notation numbers?
You put it in like times 10 to the power of.
Let me show you how I do it. And there is more than one way to do this, so if you got it down and you know how to do it and you don't want to change, that's fine. Okay? So 2.5 times, I push the times button, and then 6.022. Rather than pushing times, push this EE button or EXP, depending on your calculator. Sometimes your calculator might be times 10 to the x or whatever. Okay? EE, it's just scientific notation. I'm not sure exactly what it,
Exponential?
like, yeah.
Okay.
It means times 10 to the, and then you type in the exponent, 23. And then you push the equal button. That's it. Did you get that?
No. So you put the E after the 6.22?
Okay, does yours have this button right there? Times 10 to the x, 10
I have an X to the, and then it gives me like a box to put it in.
yeah. You might have to put parentheses around that.
Okay.
I guess it shouldn't matter on this one.
Can I look at your calculator?
Yes.
Oh, there it is.
Yeah, that's what I thought it was. It might be when you put it.
Everybody else getting this? And I can look at your calculator to make sure you got it before you leave today. But then that gives you this here, okay? And then sometimes you might be given, okay, we have 3.91 times 10 to the 25 molecules of water. And we want to know how many moles of water. Can you do that? If we have 3.91 times 10 to the 25, and don't abbreviate molecules, I know you want to because it's such a long word. What's the conversion factor? What goes on bottom?
So, trying to get the moles, right?
That's right. Got to know what we're looking for. We got to know what we know.
So the molecules would go on the bottom.
How many?
1.
Let's see. 1 molecule of H2O means we have how many moles?
6.22? No.
Now let's think about this. A mole is the amount of substance we use as the SI unit, Scientific International Unit. If one little teeny speck was the same as 6.022 times 10 to the 23 moles, we might want to pick a different unit, right? So it's 6.022 times 10 to the 23 particles, and the particle of the water is called a molecule, right? It's always the particles that's the big number to 1 mole. Are we good?
Yeah.
Write that down. Practice it more than anything to get good at it. And we can see molecules of H2O go away. We're left with moles. So now we take 3.91 times 10 to the 25, divide 6.022 times 10 to the 23, and we should get something like 64.9 moles of H2O, if I did my math right. Everybody else getting that? Doing okay? Did you figure it out?
Yeah.
Your calculator?
So you put everything into parentheses.
And then it works for you?
Yeah.
Okay, perfect.
And then we get 6.49.
So I got 64.9. Is that what you guys got?
I got
No.
64.
So the molecules are on the bottom, so you divide them by the 3.9 to the...
Nope, 3.91 times 10 to the 25.
Yeah.
That's our first number. And then it says divided by that number.
Yeah, and if you divide that, what I got was, hold on. Oh, it's because I didn't add the times 10 to the 25. So that was just my error.
We good? Everybody getting this? All right. And guys, this is the little baby steps of where we're going. So make sure you can do this. Okay? Now here's where we kind of talked about a little bit already. Any questions on that? Do we need to do another example? How are we feeling? No? One more? All right. Let's say we have 4.32 moles of carbon. And we want to know how many, what's the representative particle of carbon called? What's the smallest particle of a carbon called? An atom, right? So we want to convert this to atoms of carbon. What goes on bottom? Moles, so they cancel out, good. And 1 mole is the same as how many atoms of carbon? 6.022 times 10 to the 23. Yeah, that's right. Moles go away, and we're left with atoms. So we just take 4.32 and we multiply, because 6.022 times 10 to the 23 is on the numerator. And we get a number. Someone tell me when you got it. What'd you get? 2.3? 2.6 times 10 to the what? 24? Anybody else get that?
Yeah.
And here we should have 3 sig figs, because we have 3 sig figs in our measurements. So 2.6 what? 0? There we go. And that's what a lot of us missed on the exam was, is that 0 significant?
Yes.
Yes, because there is a decimal, right? Are we good there? All right. And the next part is molar mass. What does that sound like? The mass of what?
Moles.
Of what?
Moles.
Of a mole. Molar mass, the mass of a mole. You with me? Where do we find molar mass? What's mass measured in? Grams. The mass per mole. Grams per mole. Where do we find this?
Would it be, it wouldn't be in the atomic weight, would it?
It would be.
Oh.
That's the atomic mass on the periodic table. So what's the molar mass of carbon? Pull your periodic table out. Try again. Go and trying to memorize this stuff, you're going to mess up. Don't be afraid to use your periodic table, right?
Oh, good idea.
12.01 grams per mole, right? Can I just round that to 12? Yeah, why not, right? Because 12.01 is just an average anyway, isn't it? But what about chlorine? What's the molar mass of chlorine? 35.5? If you're going to round it to 35.5. That's too far to round it just to the nearest whole number. Okay? So, how do you, what if there's a situation where you're just not sure if you should round or not? Then don't round. You don't have to round on this one either. But I usually do, just to make it simple, right? 12.01 is basically 12.
So
And-
when in doubt, don't?
That's right. And so let's see, what's the molar mass of H2O? Is H2O on the periodic table? Ooh. Can you figure it out? 18. Should I show you how we figured that out? What's the molar mass of hydrogen? 1, and there's 2 of them. Plus, what's the molar mass of oxygen? 15. Now be careful, this looks a little bit like counting valence electrons, right? Are we counting valence electrons here? No. So, don't get it mixed up, okay? What? That's right. So that's going to be 18. Does that make sense, guys? Well, let's do a little bit harder one. Let's do strontium nitrate. Can you find the molar mass of strontium nitrate? What's the molar mass of strontium?
87.7.
87.7. How do we do this bunch?
You do three. You do one nitrogen and 3 oxygen.
And then you multiply that by 2. Order of operation says 3 times 16 first, right? Which is 48 plus 14. 60. Is it 62? Multiply the 2, and that gives us what? 124. And we add those together, and we get 211.6. Does that make sense, everybody?
Yes.
Did I do my math right? Because I mean, did Vir do his math right?
No, he was wrong.
The last one.
211.7.
Oh, okay, ish. 7? All right. And then what is this? It is the molar mass, but okay, big deal. Who cares? What do we do with this?
Convert them.
Yeah, it's just a conversion factor. That's all it is. We have 211.7 grams of strontium nitrate for every 1 mole of strontium nitrate. Or we can flip it. 1 mole of strontium nitrate for every 211.7 grams of strontium nitrate. And we use whatever conversion factor is going to help us to cancel out the units and leave us with the unit we're looking for. Where can you find these conversion factors? On the periodic table. Loads of them. And the compounds, there's thousands of different compounds. We can calculate the molar mass for those. So we're converting grams to moles because you guys ever have a measuring device that measures how many moles you have? Has anybody ever seen those? That's because they don't exist. Why do we have moles? It's to make predictions. And we're not going to get into it all the way today. Probably next unit we'll get into it a little bit deeper. Actually, no, this unit. Toward the end of this unit. Okay? Okay, let's say we have 3.51 moles of sodium chloride. And we want to know, well, how many grams of sodium chloride is that? Because which is more useful, do you think? Moles or grams?
Grams?
Grams is a lot more useful. We can measure out that, right? But we can't measure moles, so start with 3.51 moles of sodium chloride. And what goes on bottom? 1 mole of sodium chloride for every 23 plus 35.5, which is 58.5 grams of NaCl. You with me? Did I do that too quickly? Moles go away, leaving us with grams. 205 grams of sodium chloride. That we got?
Did it backwards.
You did?
Yeah, I divided by moles.
So, how do you make sure that you don't make that mistake?
Pure dyslexia.
Oh, okay. Probably. Okay, I'm just wondering, did we not write the units?
Yeah.
Are we writing this down? Okay, good. I mean, that's what I was going for. Sorry about that.
So moles on bottom is multiply and moles on top is divide.
Yeah, you multiply by the guys on top, and you divide by the guys on bottom. Since it's just one on bottom, we don't have to worry about it. Or if you want to multiply all the guys on top and get an answer, multiply all the guys on bottom, get an answer, and then divide them, like we learned in 6th grade, right? We can do that. Does that make sense to everybody? You want to do one more? No? We're done? We got one more little piece and then we're done with this. We made it all the way through. Let's do it.
All right.
But do you want another example of that first? So we can go to grams to moles or moles to grams, right? The same conversion, you just flip it. Are we okay with that? Okay. So the next part is more cool than anything else. Okay, so let's say we have 1 mole of oxygen gas, and if we have 1 mole of gas, what happens if we put it in a container that's this big? It's going to fill that container, right? If we put it in the container as big as this room, what's it going to do? Fill the entire room, right? So, what can change that besides, let's say we get a container and we're not going to get a different container.
How does it do that when it's just one measly mole?
Because gas spreads out, goes, right? Gas is not, remember we talked about intermolecular forces? Gas doesn't have intermolecular force because they're so far away, right? So far apart, and so they're not attracted to one another. They're just kind of pushed out. But if we have a condition where we have the constant temperature and constant pressure, let's say we have 1 mole of oxygen gas at 25 degrees Celsius. This is room temperature. And let's say 1.5 atmospheric pressure. If that stays constant, then the volume should also be constant, whatever it is. Let's say, and this is wrong probably, but let's say this is 3 liters or 3 milliliters. Okay? If we have 1 mole of hydrogen gas at 25 degrees Celsius and 1.5 ATM, guess how much volume we have? 3 milliliters. The same. Now, we can do this for infinitely different combinations of volumes and pressures, right? We're not going to. But if it's the same temperature and same pressure, the volume of any gas is the same. Isn't that cool? All gases work the same. They behave the same way. But there is one that we figured out. So at standard temperature and pressure, where the standard temperature is 0 degrees Celsius or 273 Kelvin, right? And the standard pressure is 1 ATM at sea level, right? So we call this STP, standard temperature and pressure. 1 mole of any gas fills a space of 22.4 milliliters. No, not milliliters. Ooh. Been a while. Liters. 22.4 liters. Good? So, is this wrong? Probably, right? Do we need to know that? No. What do we need to know here? When at constant temperature and pressure, the volume of gas doesn't change no matter what gas you have. Does it work for anything else besides gas? No, it's just gases. Okay? Is this a conversion factor? Right here? Yes, but only works for standard temperature and pressure. Come on. Okay? And then it's just another conversion factor. Write that down. You may need to know that for the Unit 3 test. So I just gave you a bunch of conversion factors today. Are we good with converting? Can we do this? All right. 2 minutes over, I'm sorry.
It's okay.
But we're done. If you want to look at your exam, you can either see it right after class, or if you want to meet another time, let me know.
Can we do it like, if I come early next
Yeah.
class? Wonderful.
Yep, perfect.